We are now at the second part of the topic of collision in mechanics. In the last part, we have seen that at last part we have actually seen the topic of totally elastic collision. We have seen the topic of totally elastic collision, where we have found that the relative velocity of approach is equal to relative velocity of separation. We have also seen the condition of some special cases where both masses are same, where one of them is static, etc., etc. In this class today, we shall discuss the partially elastic collision. Partially elastic. Partially elastic. Elastic collision. As I told you also that theoretically, all collisions are partially elastic. But for the purpose of our practical approach, we call many of the elasticity, if they are pretty good elastic, we call it elastic collision. So let's see what happens in partially elastic collision. We have seen in fully elastic collision or perfectly elastic, condition. In a perfectly elastic collision, what happens? There are two bodies, M1, M2, and they move. And after some time, they collide. And we assume that there is no deformation of these two bodies during collision. And then again, they separate and both of them move. This was perfectly elastic. And partially elastic happens. This is one body, say this is M1, velocity of U1. It is another body, M2, moving with a velocity of U2. And we assume U1 is more than U. That means M1 moves faster. So after some time, they will collide. So they collide. But it is partially elastic. So when they collide, they are a little bit deformed like this. They are a little bit deformed like this. But anyway, they do not stick to each other. So they separate once again. So this is M1, moves with the velocity of V1, and this is M2, a little bit the velocity of V2. This is the partially elastic condition. So here, mind it, they are deformed during collision. There is a deformation. There is a deformation of the shape of the body during collision. Deformation means there is a potential energy. Both M1 and M2 gains potential energy. And it is clear, since there is no external force, since there is no external force, so this potential energy A is at the expense of kinetic energy. That means both of these had some kinetic energy before collision, and both of them will have kinetic energy after collision, but kinetic energy is not conserved. Kinetic energy, so we write here, kinetic energy is not conserved. This is very important. Not only the kinetic energy is not conserved, also we should write the kinetic energy final less than the kinetic energy initial. That means there is a loss of kinetic energy. And this loss of kinetic energy is conserved in the two bodies in the form of their potential energy due to deformation. So far as their equations are concerned, momentum is conserved. Momentum is conserved. Momentum is conserved. Momentum is conserved. If momentum is conserved, then as usual, M1 U1 plus M2 U2, M1 U1 plus M2 U2 will be equal to M1 V1, M1 V1 plus M2 V2. But so their kinetic energy, so their this equation anyway holds good. But the earlier resolution of the last part, that in totally in perfectly elastic condition, the velocity of separation is equal to velocity of approach. In perfect elastic, in perfect elastic, in perfect elastic collision, velocity of separation equal to velocity of approach. But in partially elastic, in partially elastic collision, the velocity of separation, sorry, I should write relative velocity of separation. Relative velocity of separation, relative velocity of separation is less than the approach, less than the relative velocity of approach. And their ratio is given a special name. Their ratio is given a special name. Ratio, the ratio of relative velocity of separation divided by relative velocity of approach is given a new name. Relative velocity of separation is V2 minus V1, and this is 1 minus U2 because E1 is larger. This is given a new name. It is called coefficient restitution. ST, and normally designated by the letter English small e. And one thing more you need to remember that you have seen in your last class, the direction of V1, V2 depends upon their masses. So the subtraction V2 minus V1, here V2 will be larger or V1 will be larger, you do not know. So, but since it is a coefficient, so normally we take a mod of this ratio. If the ratio is negative, somehow the mod of that ratio. And this E is, of course, always less than 1 because the velocity of separation V2 minus V1 will be always less than the velocity of approach. The coefficient of restitution is always less than 1. We have seen perfectly elastic collision. We have seen partially elastic collision. Now we shall see perfectly inelastic collision. We shall go to perfectly inelastic collision. A line here. We go to the next topic. Next topic is perfectly inelastic. Perfectly inelastic. And what is a perfectly inelastic collision? Perfectly inelastic collision is like this. Suppose there is a body M1 traveling with a velocity U1 and another body M2 traveling with a velocity of U2. Once again, U1 has to be more than U2, otherwise there will be no collision. And after some time, they collide, and there may be some kind of a deformation or no deformation, and then they stick to each other. They stick to each other. And the total mass becomes M1 plus M2. And both of them moves with a velocity v. One example of this, suppose there is a ball. Suppose there is a ball which is moving and a bullet is fired. And say a bullet is fired. So what this bullet will do? Bullet will go and stick into the ball, and then both of them will move together. So anything like this, there are many such examples of perfectly inelastic collision where the body finally becomes the combined body. Sketch. in this case, considering the potential, considering the momentum, issue, what you get? M1 U1 plus M2 U2 is equal to, after collision, this is a combined mass M1 plus M2 and its velocity is v. That's it. So what do we find here? Velocity, final velocity v is M1 U1 plus M2 U2 divided by M1 plus M2. This is a perfect velocity. This is the final velocity. And here also, there is a loss of kinetic energy, because since they stick together, both of them gain a potential energy and there is a loss of kinetic energy. If you want to find the loss of kinetic energy, we can try doing that also. It's not very difficult. Say, what is the final kinetic energy? K final kinetic energy is half M1 plus M2 is square. This is equal to half M1 plus M2. And what is V? V is given by this equation, multiplied by M1 U1 plus M2 U2 divided by M1 plus M2. This denominator is also squared, numerator is also. This is equal to half of M1 U1 plus M2 U2 whole square divided by plus M2. And what is the initial kinetic energy? Kinetic energy initial. Initial kinetic energy is half M1 U1 square plus half M2 square is equal to, we take half outside the bracket, so it is M1 U1 square plus M2 square, right? Then we try to find out the loss of kinetic energy. How much is the loss, right? Then we find out loss of kinetic energy, loss of kinetic energy equal to initial kinetic energy Ki minus final kinetic energy K. Ki minus K is the loss of kinetic energy. The Ki minus K, loss of kinetic energy, we have seen this is the final kinetic energy and this is the initial kinetic energy. In both cases, there is a half. So this half we can take outside. Half we take outside. And initial kinetic energy is M1 U1 square plus M2 U2 square minus final kinetic energy is like this. M1 plus M2 and M1 U1 plus M2 U2 final kinetic energy. Right? Now, here, this is equal to the half remains outside the bracket. And, oh, let's do one thing. Let's take M1, M2 also outside. Let us take 1 by 2 M1 plus M2 outside. This M1 plus M2 we take outside. Then what we have here, M1 will be multiplied by this M1. So here we have, I think this area will be too short for this purpose. So we'll go to the line. Here we take 1 upon M1 plus M2, that multiplied by M1 U1 square multiplied by M1. So M1 square U1 square plus M1 M2 U2 square plus M1 M2 U1 square plus M2 square U2 square. Then we have minus of this. Minus of this is M1 square U1 square minus M2 square U2 square minus 2 1 M2 U1 U2. This is the total equation. Now what do you find here? This is, I have a M1 U1 square here, M1 U1 square here. Right? These two gets cancelled. Also, there is a M2 U2 square plus M2 U2 square minus. They gets cancelled. What I am left with is equal to 1 by 2 M1 plus M2 within second bracket. I have M1, M2. I have M1, M2. Now, this M1, M2, what is left to it? You see, always there is M1, M2. M1, M2, M1, M2, and M1, M2. So, what I would propose, I would take M1, M2 outside. M1, M2 outside. So, what I am left with inside is U2 square, then from here, plus U1 square plus U1 square minus 2 U1 U2. 2 U1 U2. This is equal to M1 M2 divided by 2 into plus M2 multiplied by U1 or U2, U1 minus U2 whole square. This could be written as U2 minus U1 whole square also, but we write U1 minus U2 because we know U1 is large. Now here, just note here that now we make a few comments here. Right here, M1 is positive. M1 is positive. M1 is positive. M2 is positive. And a square value, U1 minus U2 or U2 minus is always positive. Is positive. If everything is positive, so we started with Ki minus Kf. So Ki minus Kf is positive. That means that means there is a loss of kinetic energy. In fact, this is where your chapter of collision ends. But I want to just give in before going to numericals. I want to give one caution to you that whenever you will try to solve the problems of this collision and you consider the momentum or conservation of momentum, do not forget that momentum is a vector. So I write, do not forget that momentum vector. Why I give you this caution? Many times you will find that body moving in this way and another body, it may be static or it may be moving, whatever it is, and they are moving, and after some time they collide, and then finally you will find that the second body has maybe has broken into two pieces. One piece going in this direction and another piece may be going in this direction. There are the two pieces of the second body, and the first body continues to move in the forward direction as it can, or whatever it is. The first body also can go in a different direction. So in all such cases, the momentum has to be split out into x and y direction. You can take any two perpendicular direction, but x and y is normally what we all do. So here the momentum is in x direction, here is also x direction. The sum of these two momentums will be equal to sum of this x direction momentums. And y direction momentum, their sum also will be zero as a vector. That means their magnitude will be same, but direction will be opposite. So they will be automatically zero. So in your numerical problems, you will very often find that the object breaks into two or more pieces. In that case, you always have to take care of the momentum in rectangular directions, right? So this is where we finish our chapter. Next, we shall start doing the numerical examples.